Welcome everybody. This is the fifth lecture and today we will talk about non-determinism. So far we have talked about the computational model deterministic finite automata. In a deterministic finite automata, from a given state on a given symbol, there was a unique state in which the computation proceeded to. Okay. So, from a state q on a symbol A, the computation always went to a unique state. Okay. But what if we try to generalize this theme? Okay. So, today we will talk about the concept of non-determinism. What happens in non-determinism is that from a state on an input symbol, computation can proceed along multiple different paths. So, it can go to multiple states and then on each of those states computation can proceed as before. So, let us try to understand what we mean by non-determinism and how is a non-deterministic finite automata different from that of a deterministic finite automata. So, today we will not give you the formal definition of what a non-deterministic finite automata is, we will do that in the next lecture, but our goal today is to understand non-determinism. So, basically the key points in non-determinism are as follows. So, in non-determinism, from a state q on an input symbol A, okay, the automaton can go to multiple states, and what we mean by the term multiple here is it can go to k different states where the number k is greater than or equal to 0. In other words, the automaton can go to 0 states, in which basically means that it does not go anywhere on seeing a particular symbol, or it can go to 1 state or 2 or 3 or any number that is more than that. Okay. So, computation happens simultaneously along each of these paths. Okay. So, now let us try to understand what we mean here. So, as I said that let us say the computation is at a particular state q, and on seeing a symbol A, it moved to several different states. Let us say it moved to 3 different states. So, now what happens? From each of these 3 states, computation will proceed at the same time to other different states. Okay. So, it is not that one computation halts and whereas the other one proceeds first and so on. The way this should be pictured is that along all these paths, okay, from all the states that the computation went to when going from q on a symbol A, it will move forward in a simultaneous manner. It will move forward at the same time. Okay. So, again when we will very soon look at an example, and this point will be clearer at that point. The third difference, the third feature of non-deterministic computations is that of epsilon transitions. Okay. So far when we talked about transitions, when we went from one state to another, it was always on a symbol of the alphabet. Okay. But now in a non-deterministic model, we can also have transitions which are labeled by epsilon. Okay. So has epsilon transitions, which means that from so let us say that if there is a epsilon transition of the form, let us say from some q I to some q j, okay, there is a transition like this, then the automaton moves to state q I and q j without reading the next input bit. Okay. So, if there is a transition of this form, then the automaton would move to states q I and q j. Moving to state q I essentially means that it stays at state q I. So, one computation stays at q I, the other moves to q j, and it does this without reading the next input bit. Okay. So, even without reading a bit, it will do this, and from there on the computation will proceed as earlier. And the last point is that of acceptance, and input is accepted if there is some computation path that leads to an accept state. Okay. So, what is a computation path? A computation path is just one of these paths that I am considering. So, whenever the computation branches off, okay, it gives rise to more than one computation path. So, if any one of those computation paths leads to an accept state, then we accept the input. If all the computation paths end up at a reject state, then we do not accept the input. So, that is the idea. Okay. So, let us look at an example. So, here is an example of a NFA. Okay. So, we have state q0, which is the start state. From q0 on a so, from q0 on a 0, it stays at q0, and from q0 on a 1, okay, it stays at q0 as well as it go to the state q1. Okay. So, here you can see that here is an example where from Q0, okay, on seeing the input bit 1, the machine goes to 2 states, that is Q0 itself and Q1. Okay. Now from Q1 it goes to Q2 on the symbol 0 as well as on epsilon. Okay, so there is an epsilon transition from Q1 to Q2 as well as there is a transition labeled by 0. From Q2 we go to Q3. On a 1, and Q3 is our accept state, and let us say that at Q3 I stay at Q3 if I see a 0 or 1. Okay. So, this is an example of an NFA. So, let us look at some of the transitions. So, as I said that from the state Q0 on a 1 we go to both these states Q0 and Q1. Similarly, if you look at another example from the state Q1, if we see a 1, where do we go to? Okay. So, look at the state Q1, there is no transition coming out of Q1 on the symbol 1. Okay. So, therefore, it is just the empty set. Okay. As I said earlier at the beginning that we can go to multiple states from a given state Q1 input symbol, which does include the number 0 as well. Okay. So, this is an example where we go to no state, hence the empty set. Another example, let us take maybe Q1 on 0, we go to a single state, that is Q2. Okay. So, these are some example transitions. Now, let us look at an example of the epsilon transition also. Let us try to see what happens. So, we have an epsilon transition from Q1 to Q2. So, from Q1 on this epsilon transition, where do we go to? Okay. So, again as defined earlier, so let us look at the definition of this epsilon transition. So, when we have an epsilon transition, the automaton simultaneously moves to the state to which there is an epsilon transition, as well as it stays at the same state, okay, without reading an input bit. So, that is what happens here. So, from Q1 we have an epsilon transition to Q2. So, the set of states that the automaton goes to is Q1 comma Q2. Okay. So, here so these are some of the example transitions. So, one point that I should make at this juncture is that the transitions are labeled with symbols from the set. So, this is usually denoted as sigma epsilon, which is basically sigma union with epsilon. Okay. So, here we have, so if you look at the labels that are there on these states, that are there on these transitions, they can either be symbols from sigma or they can be the label epsilon, okay, and this set is called usually referred to as sigma with subscript epsilon. So, we will be using this notation frequently. Okay, so now let us look at an example of an input that is accepted by this automaton. Okay. So, consider an input, let us say W equal to 0 1 0 1 1 0. So, how does this automaton? So, we have our automaton over here. Okay. So, how does this automaton proceed with its computation on this input? Okay. So, let us try to look at this. So, we will view the computation by drawing a table. First, we will have on the left hand side, we will have the set of states the automaton is in, and on the right hand side we will have symbol red. Okay. So, initially at the beginning, so even before we begin our computation, by definition the automaton is in the initial state or the start state. So, we will have Q0 here, and this is the initial state that we have. Now, what is the first bit that is being read? So, the first bit that is being read is 0, or the first symbol that is being read is 0. So, we read 0. Now, what happens to the automaton? So, on reading 0, the automaton from Q0 it stays at Q0. So, there is only one transition on 0, and that is to Q0. So, on reading 0, the automaton goes to the set Q0 itself. The second symbol is 1. What happens when it reads a 1? Okay. So, when the automaton reads a 1 from Q0, note that it stays at Q0 because there is a 1 over here. It goes to Q1 also because there is a 1 over here. Okay. So, it goes to the states Q0 comma Q1. We are still not done, okay, because look at the state Q1. So, from the state Q1 there is an epsilon transition, okay, and by the definition of epsilon transition, the automaton takes an epsilon transition without reading the next input bit. Okay. So, from the state Q1 it sees an epsilon transition. The definition of epsilon transition is that if there is an epsilon transition, the automaton will go to Q1 as well as Q2. Okay. So, there is already Q1 present here. So, we do not need to write it again. So, the automaton will go to the state Q2 as well. Okay. So, basically from Q0, on seeing the input bit 1, it goes to state Q0, Q1 and to Q2. Okay. The next bit is 0. So, we will have to analyze. So, now observe that there are 3 different computations that are taking place. Okay. So, there are 3 things that are happening simultaneously. We have one computation at Q0, one at Q1 and one at Q2. So, what happens to each of these computations? We will look at them one by one. So, from Q0 on a 0, so here we have Q0, again on a 0 we will stay at Q0. What happens from Q1? From Q1 on a 0 we go to Q2. Okay. So, we go to Q2. And what about Q2? What happens at Q2? From Q2 on a 0 there are no transitions. So, we go to the empty set, which means that I do not write anything more here. So, we just have Q0 comma Q2. So, essentially what this means is that from the set of states Q0, Q1 and Q2, in the next step the automaton goes to Q0, Q2. The next symbol input bit to be read is 1, and I will not go into the details of the analysis, you can figure it out. So, from Q0 and Q2 on a 1. So, we know that from Q0 on a 1 we go to Q0, Q1 and Q2, and from Q2 over here on a 1, if you look at the automaton, we go to the state Q3. So, we go to Q3. The next input bit is again a 1. So, again from Q0, Q1, Q2, Q3 on a 1, we go to Q0, Q1, Q2 and Q3. Okay. So, only one more bit remains, the last bit, that is a 0. So, on reading a 0, let us see what happens. So, from Q0 on a 0 we stay at Q0. From Q1 on a 0 we go to Q2. From Q2 on a 0 we do not go anywhere. Okay, so, that is the empty set, and from Q3 on a 0 we stay at Q3. Okay. So, we have Q0, Q2 and Q3. Okay. So, these are the final set of states that the automaton is in, and now does this input get accepted or not? Okay. So, the condition for acceptance was that if some computation path, okay, if there is one computation path that leads to an accept state, then we accept. Another way of stating is that in this last set of states that I have, is there an accept state that is present here? Okay. The answer is yes, because the only accept state in this NFA is Q3, and we have Q3 over here, which means that the input is accepted. Okay. So, before I proceed, I mean this concept of non-determinism is a very important concept, and later on when we will see more powerful computational models, again we would be studying at the non-deterministic versions of those computational models. So, it is very important we spend some time and we understand the idea of non-determinism, because it is basically the same for those other models as well. So, one very useful way of understanding or getting the intuition of what non-determinism is that, so think of a non-deterministic automaton as an automaton that is placed on the ground, and there is on given an input. Okay, imagine that there is some extraterrestrial being, some very powerful being, who is able to create clones of himself or herself. Okay, so, this person is able to clone himself or herself into as many clones as needed. So, whenever so this person on given an input starts at the start state, okay, and whenever it sees an input bit, it does the following. So, if on that input bit there are k many transition, this person creates k copies of itself, and in the next step each of those copies will go to these k different states. Okay. So, it has these k different copies and each of those copies goes to the k different states, and it keeps on proceeding in this manner. Okay. Suppose at some point it reaches a state, and from that state on a particular symbol there are no outgoing transitions. Okay. For example, in this case we had that from Q2 on a 0 there are no outgoing transitions. I mean, such a thing can happen, in which case that particular clone just dies out. Okay. So, that particular clone does not survive. Okay. Well, there are the other clones which are of course present there. So, this is what happens when we have a regular transition. In the case of an epsilon transition, something slightly different happens. So, if there is a from a given state, if there is an epsilon transition that let us say that from the state Q1 we have an epsilon transition to Q2, what this person will do is that particular clone will do is that. So, that particular clone, if there are k epsilon transitions going out, it will create k plus 1 copies of itself, or it will create k plus 1 many clones. One of these copies stays at the current state, whereas the other k copies will go to the k states to which we have an epsilon transition. Okay. So, it is basically the same as this. So, here we have an epsilon transition to Q2. So, it creates 2 copies, one stays at Q1, whereas the other goes to Q2. Okay. So, each of these clones basically work independently and they proceed in the same manner. Okay. So, one clone does not know what is happening with the other clone. Whenever it sees, whenever it is at a state and it sees a symbol, it just works in this manner. Finally, if some clone ends up at an accept state, okay, at the end of reading the entire input, if there is some clone which is ended at an accept state, then that input is accepted, otherwise it is not. Okay. So, this is basically a very intuitive way of understanding how non-deterministic computation happens. So, non-deterministic computation is not a natural computing phenomenon, in the sense that we cannot implement it using a standard computer, because in a standard computer we cannot create different computations at the same time. Okay. So, we have a processor at any given point of time can process only one thing, okay. It cannot process several things. Okay. So, that is why it is not a natural, but then it is very, but the reason why we study it, because it gives there are several problems which for which we get an efficient solution if we use non-determinism. Okay. We can solve certain problems in a better manner using non-determinism, and also from a theoretical point of view it is interesting because it allows us to compare with determinism. So, basically it gives rise to the question that how powerful is non-deterministic computation? Is it more powerful than determinism? Is it the same, does it have the same power as determinism? Maybe for, I mean, what happens for different models, for finite automata, for maybe models which have more resources, it allows us to compare how determinism and non-determinism behave. So, whether one is more powerful than the other or not. Okay. Okay. So, I will stop here. Thank you.